Welcome back. So last week, I started talking about how you improve performance on large scales, and it's mostly a toolbox that I'm giving to you in order to improve what you're doing. We stopped here where I give you a few tricks to avoid scaling up memory, but actually being more efficient in your use of memory. What you can do is remove unused fields. Very often in your code, you might have fields that take space in memory, but you don't use. Times billions, you can imagine all the space you can save. You can also carefully select the data structure you use. They don't all have the same memory footprint, so it's a good idea to look at them. You're computer scientists, right? So you will have no trouble understanding in depth. Do you have redundancy? Do you redundantly store the data? That also takes space. And also inheritance and runtime type detection, actually polymorphism, also takes space. So if you avoid inheritance, that's also a way to save space. How do you save CPU? If you want to avoid having to buy a more expensive CPU, then you can improve your code. For example, do you have too many method calls? Can you not flatten your method hierarchy by having longer methods? There is a fine line to find, right? One line is probably too short. 100 lines, probably too long. 20 to 25 lines, probably a sweet spot. Are you calling, again, with inheritance, overridden methods? That's expensive. Maybe you want to replace that with a switch. And of course, I hear the object orientation people scream over that. But when you do big data and billions of repetitions or for loops, then you have to sometimes think on the low level. Are you using class hierarchies that are too deep, right? Maybe an interface is going to be a bit faster. Instance of is also costly. Casting is costly. So you can design the whole thing by avoiding that. Exceptions can also be avoided for non-exceptional situations, right? An exception should only be raised if there is actually something exceptional going on. You should not use them in normal code. Then how do you avoid disk I/O? Well, this is things you already know. Use efficient formats. If you have valid JSON, it's probably a good idea to convert it to Parquet. And you can use also compression. There are versions of Parquet that further compress the columns. And by doing that, you avoid disk I/O because you have less bits to read, right? So these are also ways to be better. You can also use a binary format rather than raw syntax because you can probably get more compression in a binary format, right? But very often the binary formats have schemas. This is how they manage the compression. If you don't have any schema, then sometimes you're stuck with the text syntax. How do you avoid network I/O? Well, the trick is to batch process to avoid the network latency. You send fewer packets over the network, but the packets are bigger. So this is very often going to have an effect, a nice effect. And the other thing is called push down. What does push down mean? It means that you try to compute and aggregate the data as early as possible. For example, you can try to push down a count. It means that instead of transferring all of the data and counting at the destination on the machine that receives the data, instead of doing that, you push down the count to the machine that sends over the data, and the machine that sends the data does the count first and only ships the count over the network. That's going to save you network bandwidth. So you can pre-compute a count, you can pre-filter the data by dropping the columns you don't use in a table, pre-project, pre-aggregate. And in fact, a concrete example, and I'm actually happy that you run into that problem with RumbleDB, I received a lot of well, I saw that there was a lot of requests on exploding memory with a group by. That's an example of push down. It means that the query you wrote cannot be pushed down. And because it's not pushed down, there is an explosion in memory of all the grouped variables that take a lot of space. And the trick here, I posted a message in the Moodle forum, check that your group by, after the group by, you only use the grouping key and counts on the variables that are before the group by. Because if you do that, RumbleDB will be able to push down and throw away all of the details. It will only keep the counts from the group by. So try that. If you still have a problem, just email us. It really helps if you share your queries with us. If we don't see your query, it's very hard for us to tell. I also gave you a way to increase the memory. It's not driver memory because that would be if you use Spark Submit. But in the case of the standalone jar, Spark is already inside. So instead, you need to use the Java heap parameter, which is -xmx with the memory you need. But I give you that if you need it. But again, you don't need that actually. We have the solution queries. I executed them today right before the lecture. I checked again. It was less than 40 seconds on my laptop, less than 40 seconds. And I didn't need to add any memory. So push down, think push down, and try to understand what's going on with the group by. It's a very, very good thing that you run into these issues for that. So thanks to the push down, we can keep the shuffling to a minimum. You should try to shuffle as little as possible, but of course you cannot go to zero, right? You do need to shuffle from time to time. With Spark, you can control the size of your executors, the number of cores, the memory per executor, and the number of executors. So if you imagine you have a cluster like that with 8 nodes, and every node has 16 cores, and every node has 128 gigabytes, you could allocate 1 executor per machine with all of the cores, except 1 that's just giving a bit of breath of air to the machine to do other things. So 15 instead of 16, and 100 gigabytes also to leave some air to the machine. So we could have 1 big executor on every machine, or we could have instead as many executors per core. So 15 executors on every core and less memory. Of course, now I need to cut the memory into partitions, right? So every core gets 8 gigabytes. These are the 2 extremes. In fact, the sweet spot that you want to have is in the middle. So for example, it's roughly the square root, right? So here we could have 3 executors that each have 5 cores, 3 times 5, 15. And 30 gigabytes per executor, meaning that the 5 cores every time share within the executor these 30 gigabytes. So you really need to understand, if you use a cluster, like if you do it on Azure later, once the codes all work, you should have a spot in the middle like this, which you can set on the command line as I explained to you. Okay, now, yes, go ahead. It really depends on your query, basically. You really have, every single query is different, and you will develop an intuition over time of what works. Basically, if you have too many executors, you're wasting resources. You're going to have a lot of latency and setup. It takes time to set up executors. But if you have too few executors, you're just sequential. So you need to find the sweet spot. And this is something you develop an intuition on. So this is why we will let you play with Azure and to try things out. Okay, but even your laptop is already a good playground for these things. You can do a lot of things with 16 cores or 8 cores. Okay, so what about the size of the chunks? Here also it's a sweet spot, because in reality, you might think, okay, let's have 5 tasks and 5 nodes, and they will all nicely finish at the same time, right? Well, no, that's not real life. This is real life. In real life, everybody will finish except the last one that's taking forever. For this reason, it's a good idea to have smaller chunks and have more tasks and have multiple tasks on every slot, right? I already talked about these things. Of course, you could think, okay, let's overdo it. Let's have super tiny tasks and 1 million of tasks. This is going to be terrible, because here you have the latency. Every time you initiate a new task, that actually costs latency. So you need to find something in the middle, right? 10 or 20 tasks per slot, for example, is a good number. Okay. The network usage, network bandwidth is limited, and you want to be careful that you don't transmit too much data over the network, right? And of course, your computer scientist, it might need that at some point you just hit a dead end and you're not happy enough with the existing system, and then you just want to build the new Spark, right? And then you become in 10 years the next Databricks or the next Snowflake, which I hope one of you achieves, but this is constantly evolving. There will continue to be new technologies emerging, and probably some of you will be building them. Okay. It's already 59, so probably I will keep the tail latencies for next week, which is, I already talked to you about that. It's a very nice effect that appears at very, very large scales, the sort of scales you see in a very large company and large data centers. Let us stop here for today. Next week, I will finish that. Then we will wrap up. I will have a quick wrap up of the entire lecture. I will see if time permits, but I might try to have a quiz game next Tuesday to finish that. Why am I speaking of next Tuesday? Because tomorrow we have a guest lecture. I will not be teaching. It will be engineers from Oracle that will come and talk to you about sharding in their PGX distributed graph database, right? So please come tomorrow. They will come. They told me they will come to the main building in HGE5. We'll try to also, live stream it over Zoom. So I'll see you tomorrow for the guest lecture by Oracle. Thank you very much. Have a nice evening.